Way, and the mass is 4.5 10 to the 6. So 4 million solar masses is there in that. That region is, I forget how much it was. I think it's less than a parsec, I think, if I'm right, or maybe a parsec, maybe just a few parsec. That is the region around which, so you have million solar masses in less than a parsec size region. Size you can see actually, right? You actually have orbits of individual things. So it has to be less. It has to be less than this orbit. So that much mass in that little radius automatically means there has to be a black hole. There cannot be anything else. Whatever is there would have coalesced finally to become a black hole. So that is the this is the best evidence of a black hole in a galaxy, and that is for our own galaxy, the Milky Way. But it has now been found for every massive galaxy. All massive galaxies have supermassive black holes in the centers, and this is one of those galaxies, M84. M84, because you can't actually individually resolve the stars anymore, because these are far. You can't see anything. Only for our own galaxy we can see some stars going around. You can't do that anymore for any other galaxy. So what they do is they trace the gas motion, and that will be from the spectra. The gas is emitting emission lines, right? So you're tracing that. You're looking at the spectra of the gas, and what you find is there is this is M84, and this is a Hubble Space Telescope image, and this is where they put the slit for the spectrograph, this small rectangle thing here, and this is STIS, spectrograph on the HST, and what you see is this kind of a spectrum. So what you see is in the center. So this is redshifted, blue-shifted lines. These are giving the velocity of the line. So it's more than 400 kilometers per second. And it suddenly increases in the center. You see this very great increase. And that's because suddenly gas clouds are moving like this, redshifted, blue-shifted gas. The moment it comes close to the black hole, suddenly it goes very fast. That's what it means. Okay, this and that very high velocity in that very small region again means that there has to be a supermassive black hole. So that is how it was inferred in this galaxy M84. And in fact, it has a much larger black hole than the Milky Way, which was only 1 million. Now we're talking about almost 1 billion solar masses. So this is 3 × 10⁸ solar masses. This is the same image, M84. This was the optical image. Now this is the radio image. The red is the radio, and the blue is the X-ray. Okay, so if you look at the same galaxy at another frequency, you'll see that. So finally, we come to the model of deviation. So we have all these independent observational facts. Now we're going to put them together. So what we think, so this is of course a cartoon, because remember we cannot see anything. We cannot, no telescope can actually observe or resolve the very inner structure. Except the radio telescopes. I'm going to talk about that in the end. Because radio has this great, because you can change your resolution arbitrarily, so you can actually reach very close to the center of the black hole in the radio. We'll talk about that. So what we believe is happening in an AGN. There is a supermassive black hole which is there in all massive galaxies anyway, including spiral galaxies and optical galaxies. But there's an accretion disk around that black hole, and in this black hole accretion disk region, bipolar outflows are launched. These bipolar outflows are moving at speeds close to speed of light. The outflow itself. So it's called bulk relativistic motion. Meaning, so you have, and this outflow is emitting synchrotron radiation. I'll come to that. Which is actually coming from charged particles moving in magnetic field lines. So the charged particles in magnetic field lines are moving at relativistic speeds, but the bulk of those charged particles are also moving at relativistic speeds. Those are the two things to remember. Synchrotron emission comes from relativistic electrons around magnetic field lines, but the plasma which has these electrons is also moving at speeds close to speed of light. And that is why you start seeing all these effects of one-sided jets. Okay, so it's called the Doppler boosting effects. So those strange phenomena start happening because the jets are moving so fast. So I'll come to that. So this is just the center. In the radio, all you will see is these. You will see, and that point source, that core that you see, is nothing but actually the jet itself. It's not the accretion disk. It's just that part of the jet which you cannot resolve with your telescope. A core is, when you say core, is something that you cannot resolve anymore. You understand resolution, right? You cannot see any more details than that. So I'll show you how when you go to other radio, like if you increase the resolution of the telescope, you go closer and closer into the jet, rather than going, okay? So I'll talk about that. So this is the radio, but there are gas clouds which are around this black hole accretion system, and these are the ones which give you the spectra of the broad lines in the spectra. They're coming from these clouds. So this region is called broadline region. Okay, BLR for short. Broadline region have widths of thousands to 10,000 kilometers per second. Electron densities are greater than 10 to the 9 per cc. And I'll tell you why, how all these numbers actually come from the spectra itself. So if you use spectra, you will have the presence of certain lines, the absence of certain lines, the ratios of intensities will tell you everything about the density of the gas. Okay, so these numbers have come from the spectroscopy basically. And then you have gas clouds which are further away from this central region, and these are the narrow line regions, or these clouds are the narrow line clouds. These are the ones which give you the narrow lines in the spectrum. Okay, so you see the broad lines from the very center, narrow lines from further away. And we believe that there is some kind of dust structure which is called a torus for historical reasons. I mean, we don't know if it's really a torus, but there's some structure around the central engine which will hide the broadline clouds depending on how the AGN is in the sky. So if the AGN is like, if the jet is coming towards you, then you see the broadline region. So in the spectra, you'll see the broadlines. If the AGN is now in such a way that the torus is actually blocking your line of sight, then you will not see the broadline clouds, you will see only the narrow line clouds, right? Because it's above, narrow line clouds are above that torus. So this is how astronomers have come up with this idea of unification. Because you have so many different types of AGN, there's been effort to, so it can't be that all these different types of AGN are just completely different kind of AGN. So the authors, the astronomers have tried to kind of combine these classes, and so this is the CFET 1, CFET 2 that you see, the ones which show narrow lines and ones which show narrow and broad lines. Maybe they are the same galaxies at different orientations. So this is called unification. This is the idea is called unification, and unification requires this kind of a geometry. You have a torus in the center, which is blocking the lines of certain lines of sight are being blocked. Okay, and this is discussed in great detail by this paper by Antonucci in 1993.
Ma'am,
yeah,
I don't get a thing that the broadline regions are like discrete places in the accretion disk.
Yes,
so
not in the accretion disk, above the accretion disk.
Above the accretion disk.
Yes.
So like somewhere the density is much higher, and sometimes it's not so much high.
Yeah, the clouds have a high density.
So why should they be in discrete places?
Yes, why should they not disperse? And
yeah.
So it continuously keeps happening anyway, but more gas is somehow being generated to keep it like that.
Okay.
Eventually, it will finally go into the black hole itself.
Another thing is that how can the torus block? That thing I don't understand.
Okay, because it's optical. You've seen the optical spectra, right?
Yeah.
So if the dust is actually not letting the optical light come out.
Okay. Another thing is that we are talking so far of AGNs. Like for the AGNs, always the black hole needs to be at the center. Like
yes.
So AGN is not possible without the black hole.
No. So AGN are centers of galaxies, and centers of galaxies have black holes. So it's impossible to have. I mean, they just go hand in hand. Yeah.
Can you please go back to the
Yeah.
previous
Yeah.
I wanted the name.
What name? Antonucci? Yeah, Antonucci 93. It's an annual reviews article, but I think there will be some popular articles also. Okay, so that was one unification. That is sometimes we call it the radio quiet unification, because we're kind of unifying CFET 1 and CFET 2s. Yeah.
So, what my if black hole, supermassive black holes are a necessity, then what my conjecture is that let's say that there is a supermassive black hole. So is it the one that is emitting all this mass? Because see, black holes can only suck up all the matter.
No, they are the ones which are emitting the mass.
So
Yes.
the thing is that supermassive black holes, they can only suck up so much of mass, right? So where does the mass go? So I conjecture that it is the one that is being emitted in the form of AGN.
It is.
Okay. So it is. So then why is there a hotspot or hard spot so far off? It should be a hotspot throughout, right? Or is there something?
Yeah, they are hotspots throughout also. So if you have these, there are some sources called the young sources. For example, there are some particular kinds of AGN called steep spectral objects. There are compact C spectrum. I mean, there are a lot of AGN, all kinds of AGN. Some of them are believed to be small radio sources, and they had hotspots very close. So we assume that at some point they grow up, and the hotspots go further away.
So that hotspots also should be the centers of genesis of some object. So are there any objects forming in the hotspots, or it's just going to expand?
This is just plasma. There is nothing. There is no gas there. It's just relative to plasma. So you can't really really generate anything.
Yeah.
If you can somehow, sometimes if you're going through a very gas-rich environment, these hotspots can compress gas in the front. If they're hitting the medium, then that compressed gas can form stars, but not the hotspot themselves.
So they'll interact with
Yes,
the ISN.
they do interact with the ISN, and but the ones that I was talking about, they are much larger, intercluster, intergalactic scale. So at that point, there is nothing. It's kind of empty space.
So then can gamma ray bursts come from this interaction? Yes.
I guess, but there is reason to believe that it all comes from the center of the. It's something happening very close to the
So they
black hole
have
itself,
sufficient
not in the
power.
hotspots. Yeah.
They have sufficient power.
Yeah. So it's believed that gamma rays are coming from very close to the black hole rather than far away. And there are several reasons to believe that, because they come from a small region, etc. Again, you also need very high speeds. By the time you come to that jet speed, they're much lower. Yeah.
From the brightness profile of the radio jet.
Yeah.
Like this slide.
Next one.
Yeah. So we see the blobs, the hotspots basically.
Yeah.
And can we basically assume that the distribution of the speed inside the plasma is more or less constant, and from there we could map a profile of the magnetic field, because the magnetic field would determine how much radiation you would have. So is there a complementary picture of the magnetic field?
There isn't, because it's impossible to observe.
I mean, theoretically.
Theoretically, so what are you expecting? That magnetic fields will be
Confined in some regions which would correspond
They
to
are.
hotspots.
Yeah, that is observed even. So this I'll tell you more about that. So the synchrotron jets are one of the main important characteristics of synchrotron emission is that the emission is linearly polarized. It can be as high as 70% linearly polarized. So when you look at polarization image of these galaxies, you can actually get magnetic fields. You can get the orientations of magnetic fields. And you can see that they are confined in the hotspots they have a certain structure. I'm not covering polarization in this talk, but that's a very, very important, very revealing science, part of this Asian study. So magnetic field structures you can get, right? But you don't get magnetic field strengths, because this is all just plasma. To get magnetic field strengths, you either need the Zeeman splitting. I mean, there's some emission line, something should be there. Nothing is there. It's just continuum emission. Neutron emission is just continuum emission.
It's too hot for tech to observe the analysis.
There is no material to do it. The plasma doesn't do it. That's the problem. So you can get the magnetic field structures, but you can't get the strengths. But it is true that it's confined in certain ways. It seems to be magnetic field seems to be aligned with the jets. It's perpendicular to the hotspots, etc.
Do you understand how those the things evolve?
Magnetic fields?
Yes. As the plasma progresses.
Yeah, I think there is work on that. There is work. People are working on that. Yeah, I can actually, maybe in the end I'll show you an image of most of the work that's been done on this magnetic fields. There are several surveys, but there's one in which I'm involved in. It's called the Mojave. And if I can still recommend that you should look at this anyway, whether we come to this or not. It's called Mojave, Mojave. If you just Google Mojave radio, just this, not read, maybe one more. Let's say Astro or something. You will get a fantastic web page which actually shows how the magnetic fields are evolving. Those are real-time observations. We can discuss that.
Ma'am, two things. We know the black hole sucks up things. So why are these emissions coming?
So it's just so it's not everything doesn't get sucked up. So some of it is actually
those
being
which
stored.
is sucked up doesn't get in due to conservation of angular momentum. It's
Yes.
spread out.
Yes.
Another thing. So why should it have two directive all those
Why is it
directivity?
directive?
Yeah.
As opposed to, if you have a accretion disk, I think that will make it. It's the geometry of the configuration itself will give you
The rotation
By
gives
now.
the two.
Yes.
If that thing
Yeah.
rotates, then
Yeah,
it's
yeah,
okay.
yeah, yeah. Yes, of course, it's all rotating. It's rotating and in an accretion disk. See, the black hole, matter accretes onto it through an accretion disk.
Yeah.
So there's a disk already. It's not like matter is just falling onto the black hole. So the moment matter falls into an accretion disk and then goes into the black hole. So that structure will give you the bipolar outflows.
I mean, we're talking of things happening close to the black hole.
Yeah.
So how close are they compared to the solstice radius of the
Okay.
black
I
hole?
will talk about that. I'll talk about that. So here, so I talked about the radio quiet unification, which was CFER1, CFER2, and how you unified them was you invoke the torus. Okay? So to understand the spectra. There's another unification scheme that's happening because you are, like I said, there's so many different types of AGN. You want to kind of unify them and say not all of them are different. They're actually some of the same things appearing different. So the other unification is called the radio loud unification, which is, so these are radio galaxies, right? Now these are just radio images. So this is an FR2 radio galaxy, this is an FR1 radio galaxy, but we also see these kind of sources. Okay, and this is actually a quasar, and this is a PLI object. These are different kinds of AGNs. So there are 4 different types of AGN here in the radio. So now it's believed that, see, this particular source, there seems to be some points of high brightness, surface brightness. So it looks like these are hotspots, this is the core. So it looks like maybe this kind of object, if it's pointing close to your line of sight, will appear like this. Whereas this kind of an object will look like this. Right? Because there are no hotspots. You just see some diffuse emission, you see the core. So this is called radio law unification, and this suggests that FR1s and BLAC objects are the same types of phenomenon, and FR2s and quasars are the same type of phenomenon. This is radio law unification. And this is discussed, for example, in a review by Aryan Paduan. Okay? So earlier was Antonucci 93, this is Aryan Paduan. Okay, now coming to the equation which I just mentioned. This is just a cartoon, obviously, because we can't see all this. So this is the accretion disk. These are magnetic field lines which are threading the accretion disk and the black hole. And because of rotation, magnetic field lines are getting wound up. Maybe it started with the initial colloidal magnetic fields, and then because of rotation, they wind up. And this wound up magnetic field lines are the ones which kind of direct this plasma outflow. So the fields are kind of confining the jets, and they're making them very thin, very collimated. Okay. And so this, a lot of work on this, the theory of this was done by Roger Blanford and collaborators, and one of the papers is a very famous paper. If you really are interested in black hole jet physics, this is a paper to read. It's not easy to read, but maybe still you should take a look at it. So Blanford is Nayak in 1977. So this is a paper which describes how energy and angular momentum can be extracted from a spinning black hole, and the jet power will depend on the magnetic field strength and the angular velocity. So B square and omega square. So the faster the spinning black hole, the more powerful the jet, the stronger the magnetic field, the more powerful the jet. So that is one way we could try to explain why FR2 jets have these, FR2 jets are narrow and they stop at the hotspot, but they're more powerful, and FR1 jets are less powerful maybe because they don't have a strong enough magnetic field. So these were ideas to understand why there are these jets. And regarding another question, somebody had asked, like, are those the only types of radio sources that we see? Of course, they're not. So these are radio contour images of several radio sources, and they all look very different. And these are, some of them are called X-shaped sources, X-shaped radio galaxies, some of them called Z-shaped radio galaxies, because of the morphology. There are all kinds of sources here. These are real images. Actually all of them are radio images, real images, radio contour images. And this particular source actually seems to have like 2 black holes in the center, which means there is one galaxy and then there's another galaxy which is interacting with this. The other galaxy may not have an AGN, but it will still have a black hole. Okay, so if you have another galaxy with a black hole, that will change your it'll influence the behavior of the black hole with the radio jet, and you will see these kind of structures. This particular source is actually two galaxies close to each other. There are 2 cores here. Both of them have radio jets. Okay, so then again you'll have, here you can actually see 2 jets, and one of the jets mixed, just like they combine together. Okay, so all kinds of things are observed.
This plasma that is coming out, what is the origin of this plasma? Is it from the accretion disk?
Yeah, so the origin is not clear, but there are all kinds of theories like pair production for example,
Okay.
yeah, which could produce plasma. So there are many ideas in the literature. Okay, so why AGN? Another AGN important topic for AGN research is called AGN feedback. Okay, so what was observed was, so for example, again, this is a composite of several different frequencies. This image, this is a Chandra X-ray image. What you see is, you see this emission, which is basically saying hot gas in the center of the galaxy. Or rather, center of a galaxy cluster. This particular happens to be a center of a galaxy cluster. This is the central galaxy, there are many other galaxies. And you see these two holes, you actually see two holes in the Chandra, in the X-ray emission. But when you look at the source in the radio, you see that the radio lobes fill those holes. So then, this is what people are suggesting is, so there is a very well-known problem in astrophysics called the cooling flow problem. The cooling flow problem is that you have all these lot of X-ray emitting gas in the galaxy clusters, but since it's emitting X-rays, they should very quickly cool. Because you're giving so much energy out, the gas should start cooling. And the moment the gas starts cooling, it should start going towards the center of the gravitational potential. So gas should suddenly, like it should flow towards the center. But it's not observed. We actually don't observe it. We don't, so these kind of very diffuse hot gas stays like that in the galaxy clusters. So what is the reason for that? So now people suspect that maybe these jets are like are ejecting energy, mechanical energy into this medium and keeping this gas hot. So this is very important because your AGNs are not just like sitting somewhere. They're actually really influencing the whole galaxy cluster. They're not just like independent. They're just actually influencing on much larger scale. They have an influence. Yeah.
Question. So
Yeah.
why? So you're saying that the gas emits the X-ray.
Yeah.
And then the radio jets actually compensate for the energy
Yes.
loss.
Yes.
But then why are the radio jets exactly where there is a divide of the X-ray emission, the hole?
Yeah. So I think that the idea that it's pushed gas some. There's enough shocked plasma that it actually is pushing gas away, and then that will also heat up the gas, right? You kind of pushing the gas away. Okay. So now let's come to this portion which is related to radio interferometry, which is called VLBI. So this is the next breakthrough that happened when you could see all these. You saw the AGN model is just a drawing, okay, because you can't actually see what's happening. You see the spectra, you see the image, but the images don't have the details. The images, like I said, resolutions is 1 arcsecond. 1 arcsecond usually corresponds to 1 kiloparsec if you look at a nearby galaxy. 1 kiloparsec is much larger than, everything is happening in less than a parsec. Black hole accretion disk is sub-parsec. So there is no way you can see actually what's happening. But one way you can get closer is through radio. But remember, you can only look at emission, or you can look at matter which is emitting radio, obviously, right? So you can't see the accretion disk unless it's emitting the radio. Okay, so that technique of interferometry can, of course, like I said, you can really expand it. What if you make your baseline very large? You had the VLA which could do whatever. It can go as far as 40 kilometers. Okay, but you can use this technique called very long baseline interferometry. What it does is you can actually have a radio telescope on one part of the Earth and another radio telescope in another part of the Earth which are not connected by cables. You can record the data here, you can record the data here. Only condition is that both those telescopes should be able to look at the source at the same time. They both have to be looking at the same source, right? You observe, you record the data in 2 separate places on magnetic tapes, have very good atomic clocks which will exactly time your radiation, every signal at what wave, like you have to compensate for those path differences and lights before you get interference. So those path differences, to compensate for that, you have to have accurate time estimates, and that is usually by hydrogen maser clocks, etc. So you record the data in 2 places, then take the tapes together in some other place and correlate the data. So because of this, you can actually now suddenly, you can do this between continents. You don't have to be restricted to the GMRT. So now you can do, one telescope can be in the US, one can be in Europe, etc. So immediately you increase your baseline. So what happens when you do that? So VLBI, so now this is a radio image of another very famous active galaxy called M87. M87 is Messier 87. It's another catalog. And MET7 is like a FR1 galaxy. So you see one-sided, I'll talk about one-sided again. A one-sided jet like that, there's no emission. The other side there's no jet. Then this is the same, this is zoomed in of this. This is the Hubble Space Telescope image of this jet, which actually is now seeing the optical. So it's not only in the radio, this is also being emitted in the optical, and this is synchrotron emission also. Now you look at the center, the core, what I said, the core. The core is not the equation this. The core, if you look with BLBI, then this is what you see. The core is not a point source anymore, it again becomes a jet. It becomes a core and a jet, and it's always one-sided. Okay? And why is it one-sided? Is because because I said bulk relativistic motion in the beginning, that the bulk is moving at speeds close to speed of light. The moment you have that, then you have special relativity effects. Okay? And so you have this phenomenon called Doppler boosting. So what is actually happening is, so you know the Doppler factor is defined like this. So beta is the velocity by speed of light. Lorentz factor is 1 over minus square root of 1 minus beta square. Doppler factor is defined like this. Then suppose your luminosity in the jet was some luminosity intrinsic, meaning in the jet frame, in the frame of the AGN. But what you actually observe is Doppler time 3 plus alpha of the intrinsic. So what you observe is actually much more, 3 times Doppler. So Doppler factor, suppose it's like 10. Okay, you will observe 1,000 times brighter emission. Okay, and what you'll also see, another thing that you'll see is, this is called jet to counter jet brightness ratio. The brightness of the jet and the counter jet is determined by this. So, the larger the beta, the smaller the theta. The theta is the angle of the jet with respect to line of sight. The larger the beta means faster jet, close to line of sight, more the effect of this gets very prominent. So that's, you start seeing one-sided jets. So one-sided meaning counter jet emission is not seen at all because it's so Doppler dimmed. There's Doppler boosting on one side, Doppler dimming on the other side. When it goes away, it's actually in the opposite direction. So because of this contrast, you see only one-sided jets, because also your telescope is not sensitive enough to go. If you had a very sensitive telescope, you could still see that very dim emission, but you don't have that usually. So two things you have to remember: BLBI jets, whenever you see BLBI jets, they're always one-sided. I mean, almost always one-sided. That is why we know that jets are relativistic. See, on the VLA scale, I mean the kiloparsec scales, when I showed you those images, sometimes you see two-sided. Most of the time you see two-sided jets, except maybe in quasars, you see two-sided jets. But when you come to VLBI, now VLBI, what is it doing? Its resolution is much higher. You're going closer, so you're going to parsec scales. From kiloparsec scales to parsec scales. So you're close to the accretionist black hole system. There, the Doppler effects are more, which means the jets, when they start out, they're better. That's what it means. So VLBI jets are, they're always one-sided, which means jets start out very fast, and then they slow down with as they interact with the medium, etc. Another effect of this is, so here, for example, this is also a special theory of relativity. What you see, suppose there is some jet is moving in some direction towards close to your line of sight. What you would see is not beta. Beta is v by c. What you would see is something like this. Its apparent speed is different. Okay, and so for example, what this will do is, so this is the particular jet MET7. If you had a beta of 0.99 and a theta of 10 degrees, your apparent beta is 6.9. So it looks like it's greater than speed of light. Obviously it isn't. So this effect is called superluminal motion. This is another thing that was found in AGN. Superluminal meaning greater than speed of light. So this is not a real effect. It's an effect because the jets are almost close to, beta is not 1. It's not even close to speed of light actually. It can be even lesser. And small angle, fast jets, it looks like the jets are moving at speeds greater than speed of light. This is superluminal motion. So this slide will actually tell you each of the knots in that MET7 with the VLBI seems to move at speeds 6 times speed of light, 5.5 speed of light. So this is the actual jet in 1994, 95, 90, whatever. So in different years the blobs are moving, right? The jets components are moving at speeds greater than speed of light. Okay, so before I come to almost the end of the talk, I just again want to stress the fact that AGN are multi-wavelength emitters. Like this is Centaurus. This is the nearest AGN to us, Centaurus A. This is the optical image, radio image, X-ray image, and you see an X-ray jet here. Actually, you can actually see an X-ray jet. So what I want to say here is, all these different mechanisms, all these different radiations come from different emission mechanisms. The radio comes from synchrotron radiation. And synchrotron is just basically electrons around magnetic field lines, and if the gyration frequency is this, magnetic fields, charge, mass of the electron, then what you see, the frequency of the emission is Lorentz factor square into the gyration frequency. Okay, so this is, and in the spectrum wise, this is what you see. So when I say spectrum, I don't mean what you get from spectrography. Spectrum is energy per frequency. That's what a spectrum is. Spectrum here in synchrotron emission is called continuum spectrum. It's actually a continuum. There's no line and all that. There's just continuum radiation. So a spectrum will look like this, something like that. And this is also this is what you normally observe, this kind of a slope. So if you just did flux density versus frequency, this is what you get. This is called a power law, and it typically has a slope of 0.7 if it's defined like this, so minus 0.7, because it's in this direction, negative. Okay, this is the spectrum of jets and lobes in AGN. Okay, then I showed X-ray jets. This is another image of an X-ray jet. This is an X-ray emission. In the color is X-ray and the contours are radio. So you actually see X-ray jet. This is from Chandra. The X-ray emission, some of it is from the inverse Compton mechanism. Inverse Compton is when the electrons, very fast electrons, which are giving you this synchrotron radiation in the radio, will also upscatter low energy photons to make them high energy photons. So the low energy photons will get upscattered, and you start seeing X-rays. So this is X-ray emission. So I will not talk about this much, but basically these are called spectral energy distributions. Anyway, I'll come to that. So inverse Compton is normally seen from AGN. Then pair production, which I already mentioned. This happens very close to the supermassive black hole. So if you have a very high energy photon in a field with another photon or a strong magnetic field, then you can get positron-electron pairs from the photons. Okay. Black body radiation. Black body you already know. Thermal radiation, Matheron radiation. This will come from the accretion disks in AGN. The accretion disks will emit black body radiation. But of course you can't resolve it. Just remember that. You can't resolve it, but you can see it in the spectrum. Like if you look at the optical spectrum, it will have the contribution from black body radiation. I'll show another image where it will be clearer. Then there is free emission. So all these different things that you saw, radio, X-ray, optical, they all coming mostly from separate emission mechanisms. Synchrotron emission, inverse Compton, black body, free. Free is when you have, basically your charged particles around some positive charge will get deflected in the field of that positive charge and emit a radiation, and this is called Bremsstrahlung or free radiation. And this is a lot of the outflows in Cepheid galaxies, which are the ones which have very weak jets, can have contribution from free emission. Free emission has a different kind of spectrum. So from the spectrum, continuous spectrum, flux density versus frequency, you will have a particular slope. That slope will tell you if the emission is synchrotron or free. So I said synchrotron is 0.7. That slope, this slope is around 0.1. So from the spectrum you can make out. So finally, what you actually see, because you can't actually resolve all these different things, what you get is everything together, right? So these are two spectral energy distributions of two particular AGN. So you have to then, this is the spectrum actually. What you see is this. Then you have to fit components. So one, you have to fit a black body, you have to fit some recombination, you have to fit a power law. Everything goes into that. So there was not much interest. Like they thought they were peculiar stars or something. They didn't really associate this with anything spectacular. These type of galaxies were known as Cepheid galaxies. And what we know now, I'll tell you how this was finally arrived at, is that this center, which is now understood to be the active galactic nucleus or AGN, sometimes can be so bright that it can have a luminosity greater than 10 to 100 times the luminosity of all the stars in the galaxy. So what will happen is if you have a very short exposure of this galaxy, Cepheid galaxies, you will only see a star. And that's why quasars are called quasi-stellar radio sources, because they look like stars, they look like point sources. Only if you take a deep exposure can you pick up the host galaxy behind it. And in a normal galaxy you would have like 100 billion stars. So the luminosity of an AGN can be 100 times that, so 10 to the 13 solar luminosity. So the next thing that he noticed, apart from the fact that the morphology was very strange, was the spectra. So in the optical spectrum of a normal galaxy, this is what there are. These are optical spectra of 4 normal galaxies. And what you see is the spectrum. Spectrum is basically, the flux density versus frequency, let's say. And you see these absorption lines. So a lot of absorption lines. And these come from individual stars in the galaxy. So all of the stars, like the sun, because of the photosphere, you've seen the solar spectrum. If you've seen those dark lines, etc. So those are absorption lines. And that is just the stellar photospheres which are making up the galaxy. So this is what you would see in a normal galaxy. But what Seifert saw was, when he looked at the center of this particular galaxy with the point source, there were very strong emission lines. Okay, and some of them were very broad, like here, and some of them were narrow. So by broad, it would be like thousands, several 10,000s, even 10,000 kilometers per second. The narrow ones were a few hundred kilometers per second. Those were the line widths. So this is what Seifert saw. And these, like I mentioned, these are now referred to as Seifert galaxies. So before we start, so this work was done in the 1940s, and then it kind of lay dormant for a while. So it was only after radio astronomy was, became a field of study that this field again got prominence. So you must have seen this or a similar slide in your previous radio talks. So it was Carl Jansky's radio antenna. And what Carl Jansky found, though he was just investigating static, he found that there was another source which he could not identify with. Most of the sources were thunderstorms, either nearby or far away. But there was a hiss that he could not account for. And finally, this hiss seemed to always arise 4 minutes earlier than so basically that is a sidereal day. And sidereal day is 4 minutes shorter than a solar day, and this immediately means that it's some system which is giving this hiss is outside the solar system. Okay, so and finally we know that this is actually the center of the Milky Way galaxy. So the Milky Way galaxy is emitting in the radio, and because of Jansky, we have the unit of flux density as Jansky, which is this number, 10 to the minus 26 watts per meter square per hertz. Okay, so the next major step for AGN happened when the second very important AGN was discovered. This was 3C273. Okay, 3C273, 3C is just the third Cambridge catalogue. So these radio observatories, have catalogues. They observe the sky and they note down all the points. So this was the 273rd entry in the third Cambridge catalogue, 3C273. So the principle was, so this is the Parkes Radio Telescope in Australia. It's a large single dish radio telescope. So if you have a radio source which just rather when the moon is moving and it covers the radio source, because of the sharp edge of the moon with respect to the radio source, it acts like a diffraction edge basically. So when you have a diffraction edge, you see this kind of a pattern, right? If you remember your diffraction, the diffractions in the edge of the blade or whatever, you see these fringes, one-sided fringes like that. So this is what they observed. They were looking at this particular 3C273 radio source, and they found this kind of diffraction pattern. In fact, the diffraction pattern was complex. It seemed like it was not just one point source, but it actually had two components. So component A, component, because as you can see, there is a secondary bump here. So the diffraction pattern itself showed, so they could not actually image, the 3C273 was like a point source in the radio sky. But they could see that even though it was a point source, there seemed to be components, there was some structure in this point source. Okay, so from the diffraction pattern they could make that out. So this work was going on in Australia. At the same time, in the US, 3C273 was being looked at in the optical. Okay, so these two studies were actually completely unrelated. They were happening around the same time, on the same object, but unrelated. Actually, maybe 3C40, there's another quasar which was also being studied at the observatory, in the optical observatory. So what Martin Schmidt had found in, this is 1963, so this is the spectrum of hydrogen. So you see the emission lines and you see H beta, H gamma, H delta. So this is kind of a standard way the lines are arranged in a spectrum, right? There is only that much separation between lines. There is a how much broadening, how much intensity. There's a very set template for hydrogen. Okay, so what they found was that when they looked at 3C273, it seemed to show the hydrogen spectrum, but it was not exactly at the rest wavelength that we were expecting. So they found that the exact hydrogen spectrum, but it was redshifted. Okay, and so they found that 3C273 actually had a redshift of 0.138. This is supposed to be a very large redshift, which immediately means it's an extragalactic object, and this redshift, as you would have learned, is not its cosmological redshift. It's not actually that the source is moving away from us. It's cosmological redshift because the universe is expanding. So one work there which found that 3C273 was a point, which was not a point source. It had some structure, and then 3C273 had a very peculiar spectrum, just like an AGN. And this is where the field of AGN studies took off. Okay, so now much more recently, for example, this is the Hubble Space Telescope image of 3C273, and so this is how it would look in an optical image. Yeah.
How do you know that the redshift is because of the expansion of the universe, not because it is moving?
Okay, that's another story. But now galactic redshifts are all because of cosmology rather than. But we can talk about that. We'll talk about that later. Okay, so in an optical image, this is how it looks like a star, except that this actually has a jet-like structure. But people were not able to understand what this jet structure was. So with the Hubble Space Telescope, what they did was they actually put a kind of a coronagraph. So you cover the point source in the center, which is very bright. The moment you cover it, you see the background galaxy showing up. Okay. So unlike the previous galaxies, Cepheid galaxies, which you saw was spiral galaxies with a star on it. This object, 3C273, was an elliptical galaxy with a star on it. Okay, so now we know that. So Cepheid galaxies were in spiral galaxies, and 3C273, which is a quasar, which I'll talk about more, was an elliptical galaxy. Okay, so before we get into, further observations of 3C273, it's important to stress that, see, the early observations were done with a single large telescope, which is not enough to image. You can't image the radio source. That is why you had to rely on the diffraction and infer indirectly the two components. So for example, I'm sure you've seen this equation, these things before as well. Like even a very small optical telescope, even a 6-inch optical telescope has a resolution of 1 arcsecond. Okay? But even a 300-meter radio telescope, this is the Arecibo telescope in Puerto Rico, has a resolution of 173 arcseconds. So it's much, much worse. And for example, this is the latest large telescope called the FAST, which is in China, which is the 500-meter. But in spite of these large telescopes, you cannot resolve or you cannot image your radio sources. So what you would need is, if you wanted 1 arcsecond resolution to match the optical, at let's say some frequency of 1.4 gigahertz, you would need a telescope which is 54 kilometers in diameter, which is impossible to make. You can't make 54 kilometer single dish telescope. So that's why radio interferometers were born. And they were invented. And this is the very large array. So we are now, because of this technique of radio interferometry, what the resolution now doesn't depend on the diameter of the single dish, but the largest separation between the telescopes, which is called the baseline. So the longest baseline. So the fact that, you see rails here, so you can actually put these telescopes back on the rails and expand this Y. So you can change the resolution of your telescope. So the resolution now is lambda by B rather than lambda by D, which is the diameter of the telescope. B is the baseline. So you can actually make it much larger. So for example, in the A array, which is one of the configurations of the VLA, at 1.4 gigahertz, you will get 1.4 arcseconds. But if you go at a higher frequency, because resolution is lambda by high frequency, you will get a better resolution. So you are now artificially, in some way, creating, you are able to increase your resolution in an unlimited manner. This is the best thing about radio interferometry. And I'm sure this is also familiar to you. You must have done this already. This is how, because of the Earth's rotation, this is how the array would appear if you were a radio source. If you were looking down at the array from a radio source, this is how it would look. So it already starts looking like a big telescope, like a big diameter, a large telescope with a diameter which is equivalent to the largest baseline. So this is how you create apertures. This is aperture synthesis technique. So once the VLA came into the picture, once the VLA started functioning, this was in the 1970s. So 1963 is when you did the lunar occultation 3C273 measurements. Once you had the VLA, you could actually image it. So then, when they imaged 3C273, this is what they found. So actually, what was there? This is the center of the galaxy. I will tell you more about these types of sources. This is the center of the galaxy. This is what is called a hotspot. You can't see it very clearly, but there is a very bright point source here. So these 2 point sources were the ones which were showing up in the diffraction pattern, the component A and component B. Okay. So similarly now, because of other radio telescopes which do radio interferometry include the GMRT, for example, and you've already visited GMRT last weekend, yeah. And so 30 antennas of 45 meter diameter, and again the array is in a shape of a Y. And in the future, you would have the square kilometer array. This is just an artist's impression of what the square kilometer array would look like. And these are actual images of telescopes, where these are what are known as precursors to this SCAR. Basically, they're testing new types of antennas which will be used for SCAR in places in Australia and South Africa. So these are known as SCAR precursors. So that work has already begun. Okay, so now coming back to AGN. So one of the most important, like the majority of the work in the study of active galaxies has been done at radio frequencies, and you can understand why, right? So this is now both these images are actually what are known as overlays between radio, optical, everything. All the different frequencies are over. So what you do is you take an optical image, you take a radio image, you superimpose them, right? And that's what's been done here. So this actually is three frequency image. So at the green thing that you see is the optical image of a spiral galaxy. The red that you see is X-ray emission from Chandra X-ray Observatory. Okay, hot X-ray emitting gas, and the blue that you see is the radio emission. So you see a core jet structure, but much smaller. It's much smaller than the size of the galaxy itself. So this is a typical this is a Cepheid galaxy, NGC 1068, and this is what Cepheid galaxies look in the radio. So we saw Cepheid galaxy in the optical, we saw the spectra. This is what a Cepheid galaxy looks in the radio. So you see a radio, 2 radio jets, but they're very small, they're tiny, just a few kiloparsec from the center.
They might be looking small because of the parallax, right?
Not parallax, you mean the projection, like if they're pointing towards you.
Yeah.
Yeah, but that's not true for all the sources. So most of the sources seem to be small. So you would imagine that there'll be a range of angles through which you'll be observing, right? So most of the Cepheid galaxy jets are small. On the other hand, you have these sources. So this now, again, blue is the optical image, and this is the host galaxy, which is an elliptical galaxy. You can see this around here. But the radio emission is seen in the red. You see these twin jets again, but they are much larger than the size of the galaxy itself. So the galaxy would be, let's say, a few kiloparsec. Like the Milky Way would be, we are like 8 kiloparsec from the galactic center, etc. So just tens of kiloparsec is the size of a normal galaxy. But these would be 100 kiloparsec to a megaparsec. So a million kiloparsecs. So that is the size of these radio sources. And such sources like 3C273 also. 3C273 is one of those objects which are actually kind of close to your line of sight. But if those kind of objects are in the plane of the sky, meaning if they're not pointing towards you but they're like this, then they'll be much larger. So this is one of, these are called radio galaxies. Now this is the center of the same radio galaxy. So this is now a Hubble Space Telescope image of the optical. Yeah.
So if these are megaparsec big,
yeah,
these are radio loud sources.
Yeah.
So if we were to point a radio telescope in the sky, we should not see galaxies at all because we should be seeing only AGNs.
Yeah, you should see mostly AGNs when you do radio.
Why do we see other sources at all?
No, why not?
Because AGN should overshadow most of the things, right? Because radio loud and...
No, but what you're forgetting is that these are not very close to each other. I mean, you can see it from the optical image itself. There are not that many sources in that field which will be emitting the radio. So they will not like block anything. And it's very rare.
We should not.
You won't have that density in the sky is not so much that it will completely.
Okay. And are we even able to image the host galaxy at all, or it's only the AGN lobes that we're able to host?
In the radio, you will only see the lobes.
Lobes, not the radio galaxy.
No, that will be the optical image. So you have to find out what. So that's why I'm going to come to that emission mechanisms. You have to see what is emitting what. Optical galaxy will emit in the the host galaxy will emit in the optical. So you will see. You have to look at the optical telescope or optical image of the same. Radio telescope will show you just this. So this is a little bit, maybe this is kind of, there should be no misunderstanding. I mean, obviously you only going to see one of these. Like this is, everything is like superimposed, right? You are combining your optical image, radio image and X-ray image. But at one time you only have one image. So you'll see these. I'll show you another one, image.
Ma'am?
Yeah.
So why there are gaps between the jets? So even...
You mean here?
Yeah.
Actually there are no gaps, but some, this is just because it gets dim enough that you don't pick up. So your telescope is not sensitive.
But actually in some jets we see the gaps.
Yeah, that I'll tell you about. Yeah, so we'll talk about that. Okay, so so these kind of sources are radio galaxies, these are Cepheid galaxies, and these are the majority of AGN. Most of the active galactic nuclei are like this, small jets in spirals. Only a small fraction, 10 to 15%, are like this, large jets in ellipticals. And these are known as radio quiet AGN. They're not actually radio quiet, but there was a definition, this is a historical thing. They were called radio quiet AGN because radio emission was not so much compared to the optical. And these were called radio loud AGN. But actually there's radio emission in both. Okay. So the other thing that was found was these radio quiet were mostly in spirals and the radio loud were mostly in ellipticals. Okay. So this is another problem. This is also the research this is the research area that I work in, which is that these radio sources. Now this is a radio image, only the radio image. So this is what you would see actually. If you aimed your GMRT to the sky, this is all you will see. No optical emission, obviously, right? So you don't see the host galaxy. You just see this. So what is seen is that majority in most of the cases, the morphology seem to be two types, as you can see from here, right? So the two types are in one case. So this is the center. This is called the core over here. This point source here is the core. You have so in one case you have jets, and then they end up in regions called hotspots, and then there is the plasma is behind it. This is called the lobe. So here you have the lobes here. But in these cases, the jets, you see two-sided jets, but there is no termination point. There is no hotspot at the end. It just goes on. So brightness is very high in the center near the core, but then it just becomes it fades away in the distance. So these are the two types, two primary types, and these were discovered by Fanaroff and Riley. These two people, Fanaroff and Riley, and so that's why they call Fanaroff-Riley type 1, this is type 1 and this is type 2 sources, or in short they are called FR1 and FR2. Okay, so this is a very active area of research. The question is why these two? Why these two different structures? And they both found in elliptical galaxies. So we're talking about the radio loud AGN. Radio galaxies in elliptical galaxies. Why do they have these two morphologies? That's a very important unresolved question.
These are the only two morphologies found.
No, there are others. I'll show you the others also. But these are the two primary, very distinct morphologies. Sometimes you will also have, which will be something like a mixture of these two. So you may have something which is like a jet like this on one side, but a jet like that on the other side. So it can be that. But there will also be much more complicated morphologies. But this is the two primary. Yeah.
In the type 2.
Yeah.
Is the jet coming from the core itself, or?
Yeah, from the core itself. Yeah. So this is the AGN. The core is the AGN, and the jets are coming from the cores. Okay, so then first question is why only 15% of all active galaxies have these large scale structures, and second is why do they have these different shapes? And also actually when you took a look, if you suppose you get the total radio power, total radio luminosity, this type of source has a higher radio luminosity, the FR2 sources. So that's another question. I mean, why do they have these distinct shapes and why do they have different powers? So those are unresolved questions in AGN astrophysics. Okay, now so I showed you the initial spectra of that Cepheid galaxy, right? And I showed you a little bit about the 3C273 spectra. Now we know that, of course, the main characteristic of an AGN is that you should see emission lines. Okay, that's one of the signatures of an AGN is emission lines, strong emission lines. But emission lines also can be like all kinds of different shapes. Like radio, I just showed you two shapes. There are many more. And the emission line spectrum also is very varied. So actually now we have identified several types of spectra, which are all AGN. So for example, these two spectra are from two different types of galaxies. They are both Cepheid galaxies, but one of them is called a Cepheid 1, which is the one which has these broad lines. thousands, 10,000s, rather let's say thousands to 5,000, as much as 10,000 kilometers per second. These are the broad lines, and some of them don't show broad lines, just show narrow lines. And these, so this type is called Seyfert type 1. This is called Seyfert type 2. So Seyferts have further sub-classification based on the spectra. Then you would have a particular radio galaxy would have this kind of a spectrum. This is a broad line radio galaxy. There are other radio galaxies which don't have broad lines, which are called narrow line radio galaxies. This is a normal galaxy spectrum. This is what is known as a liner. It's also an AGN, no ionization nuclear emission line region. So there are many types, and then you have a quasar like that. A mean quasar has a spectrum like this, like 3C273 would have a spectrum like this. And there is another type of AGN which is actually kind of going against the whole your definition of AGN, is in that it doesn't show any emission lines. No absorption, absorption also very little, but just almost a lineless spectrum. It's just flat like that, the spectrum. So this is a type of AGN called BL-like object. So we'll talk about that also. So there are a lot of variety in the AGN spectrum. And the other thing that you already saw in the previous slide where I showed you the overlays is that AGN are another characteristic of AGN. They emit over the entire electromagnetic spectrum. Okay, so they would emit in the radio, but they would also emit in the infrared, visible, X-rays, gamma rays, everything. So any telescope you point to the sky at an AGN, you will see emission. Okay, that's very rare. If you look at stars, you will see the black body spectrum, you will see the optical emission, but you may not see radio emission, for example, or X-ray emission, depending on what type of star it is. But an AGN, so like a star which looked like, or rather an AGN which looks like it's a star, will be completely different in that it will emit at all radiation, all wavelengths in the electromagnetic spectrum. That's another characteristic of an AGN. Okay, and to remind ourselves that on the ground, you will only get radio and optical bands, right? Everything else you have to go to the space. So you would need, so for example, this slide was all the NASA telescopes. So you would need this is the Hubble Space Telescope, Chandra X-ray Observatory to observe the X-ray. Then you would have gamma rays with Fermi Telescope, and only the optical will reach you and the radio will reach you. Okay, so this is a very famous AGN called Cygnus A. This is the proto, when you want to say AGN, Cygnus A is like the thing that always pops up. Cygnus A is one of the very few, so it's a nearby AGN, and again this is an overlay of several different wave bands. So here the blue is actually the X-ray from Chandra, and this is the VLA image in the red, the radio image. And you can see it's just really beautiful because you can see there is a lot of structure in the lobes. If you can see these filaments, and this is all real. Okay, and then the middle one is actually a Hubble Space Telescope image, and then the larger image is from the digitized sky survey. Okay, so finally what's the blue? Blue is the X-ray from Chandra. Okay, so before